Good morning. Today we are going to discuss about discrete time Fourier transform. So last class I have given a small introduction to discrete time Fourier transform and solved a problem, but I have not completed it. And today I will once again review the topic we discussed last class, that is discrete Fourier transform, and I'll once again solve the problem and we'll proceed further now. So already told you that discrete time Fourier transform is mainly developed to represent a periodic sequence, because Fourier series techniques are mainly used to represent periodic signal, and it's very difficult to represent periodic signal using Fourier series coefficient, since we are using Fourier transform, that is discrete time Fourier transform technique, to represent aperiodic signal. When we are discussing about discrete time Fourier transform, we need to uh, know uh, Dtft pair, that is analysis and synthesis equation. So analysis equation is used to take discrete time Fourier transform of a given sequence x of n, and synthesis equation is used to recover or take inverse discrete time Fourier transform of a of this Dtft of a given sequence x of e power j omega. So this is two important equation we need to remember when we are solving problems related to Dtft. And of course, I just want to tell you important things related to the equation. Some Oppenheim and Schaffer, they used to call Dtft like x of e power j omega, but we have a lot of textbooks related to signal system, and you can even find some books may represent like x of omega, capital omega, and equation both are same, but the representation is different. Instead of using small omega, they may use capital omega to represent Dtft, as well as inverse Dtft. So you don't need to worry about this notation, and you can study the book and refer books for different kind of problems. And don't ask me why they have used capital omega and here they use e power j omega. Both are same, okay? And to in order to give a difference between two different books, they might have choose to capital omega or small omega, something like that, okay? And both, there is no change in the equation. Both are exactly same equation except the notation. That's it. So with this small introduction about Dtft and the Dtft pair, we are going to solve a problem. So the problem says, consider a signal x of n is equal to um, just a minute, I will admit 2%. So consider x of n, which is equal to a power n and u of n, and magnitude of a is less than 1. Magnitude of a is less than 1. Okay. And determine Dtft of x of n and plot the response. This is the question we have. First of all, we have to write the formula to find out Dtft. The formula to find out Dtft is x of e power j omega is equal to summation n is equal to minus infinity to plus infinity x of n into e power minus j omega n. Now you have to substitute the value of x of n. X of n values here. We are going to substitute the value of x of n here. When you're substituting a of n in this equation, I'll get summation n is equal to minus infinity plus infinity a power n and u of n e power minus j omega n. Here we have a step function. You know what is a step sequence? Step sequence starts from 0 and it will go up to infinity, but actually we have a limit, that is summation limit, from minus infinity to plus infinity. Because of the multiplication of step sequence, the range of summation reduced to uh, 0 to infinity from minus infinity to plus infinity. So I am changing the limit. N is equal to 0 to infinity a into e power minus j omega into n. So we need to solve this equation because this is an infinite series. You have to go, it will go up to infinite starting from 0. When you are expanding this particular expression, you will get 1. So when you are substituting n is equal to 1, n is equal to 0 in this equation, you will get a and e power minus j omega power 0 plus a and e power minus j omega power 1, and it will go up to infinity. And it is very important to find out the value of x of e power j omega for different set of, that is n is equal to 0 to infinity. It is not possible because it's an infinite series. Hence we are going to use standard formula to find out the value of x of e power j omega. For that we are going to use geometric series. And this series says, when you come across a infinite series something like this, that is summation n is equal to 0 to infinity x of n, then this can be written like 1 by 1 minus s. So this is a famous equation we are going to use to solve this problem. Here x value is a into e power minus j omega. So x power n. So this series will go up to infinity. So what I am going to do it, I am going to use this formula to reduce this infinite series into 1 by 1 by 1 minus x. X values is a into e power j omega. Hence the value of x of e power j omega is 1 divided by 1 minus a into e power minus j omega. Okay, so and of course I have given a few more problems to reduce the infinite series, like when n is equal to you can take the second equation, summation n is equal to 1 to infinity n into x power n minus 1. If you come across this kind of equation, then you can reduce this equation using this formula 1 by 1 minus x the whole square. Similarly the last one, third one, and you can even go up to some in different way. But anyhow, we are not going to bother about higher order, or we are going to bother only first and second one. So we have determined discrete time Fourier transform of the given signal x of n is equal to a power into u of n. Now the condition given is magnitude of A is less than 1. Magnitude means already we know that magnitude, it includes negative and positive. For this particular case, A can take value from 0 to 1, except 0 and 1, the remaining values it will take, because magnitude of A is less than 1. So I can simply say the condition of this A is in between 0 to 1. So it won't take 0 as well as 1. So I can take condition is 0 to 1. Now we are going to find we are going to plot magnitude and phase response for this particular case. For that, it's a complex, since it's a complex number, what we are going to do is we are going to separate real and imaginary part to find out magnitude plot and phase plot. For that, I am going to write x of e power j omega, x of e power j omega is equal to 1 by 1 minus a into e power j omega into, so I'm just expanding e power j omega like cos omega minus j into sin omega. I'm simply substituting the value of e power j omega using Euler's theorem. So the equation will be like 1 by 1 minus a into cos omega minus j sin omega. Now I am going to separate real and imaginary part of the denominator. Then I'll get 1 by 1 minus a cos omega plus j into a sin omega. Now we have a complex number in the denominator, but I require only real part and imaginary part. In order to separate real and imaginary part, the general procedure is to multiply and divide this equation by complex conjugate of the denominator, that is this denominator function. I have to take a complex conjugate and I need to multiply and divide using that equation. So what I did is I am taking complex conjugate of the denominator. I will get 1 minus a into cos omega minus j a sin omega. I am multiplying and dividing. After doing this, I am completely multiply the equation inside the left hand side. I'll get I'm just multiplying it and I'm separating real and imaginary part. What I will get is 1 minus a cos omega divided by 1 minus 2a cos omega plus a square. This is the real part of the complex number minus j into a sin omega divided by 1 minus 2a cos omega plus a square. This is the imaginary part of the given complex number. So I have given the proof for how I arrived 1 minus a cos omega plus a square, that is denominator part. Okay, this one I have given here. Okay, just have a look. Okay, so I have separated real and imaginary part. Now I have to draw magnitude response and frequency, phase response. So this is the plot of magnitude and frequency response. So for magnitude response for the case of a is greater than 0, first one. So first I am going to consider a is greater than 0. For this particular case, what the plot looks like, I have function x of e power j omega is equal to 1 by 1 minus a d power j omega. Now we are going to substitute different values to this omega. I am going to take omega in x-axis and magnitude of x of e power j in y-axis. So I am going to give different values to this omega and plot the graph. First of all, I am going to substitute omega is equal to 0. When I am substituting omega is equal to 0 in this equation, I will get e power 0 is 0. So the maximum amplitude of x of e power j omega is 1 by 1 minus a. At the same time, I will get minimum value when omega is equal to pi. When I am substituting omega is equal to pi, I will get minimum value, that is 1 by 1 plus a. Okay, 1 by 1 plus a. So we have to connect all the points to draw the graph. So this is the magnitude plot when a is greater than 0. Next we have to draw phase plot. For this we should have a equation phase plot. So phase angle of the given complex number, that is response, is minus tan inverse of imaginary part by real part. For that I am going back to previous slide. So here imaginary part is a into sin omega divided by 1 minus 2a cos omega divided by real part 1 minus a cos omega divided by, so these two will get cancelled and I will get only a sin omega divided by 1 minus a cos omega. For this case, when you are substituting omega is equal to 0, Sine omega is equal, so tan inverse of when omega is equal to 0 in the phase angle equation, you will get 0, and you will get maximum value when pi by 2 or something like that, and whenever you substitute 0, pi, 2 pi, and 3 pi, 4 pi, something like that, for all these values, the value of the phase plot will be equal to 0, and it will reach the maximum for, it's very close to 0 and negative 0. Now 0 and left hand side. Okay, so this is the magnitude and phase plot when a is greater than 0. At the same time, when a is less than 0, you will get a small change in the plot, that is magnitude plot, and there will not be a big change in phase plot, but what will you will get a mirror reflection with respect to x-axis. Just see these two plots. So here after 0 you have a negative plot, but here you have positive, and that is a mirror I can even say that is delayed version of the plot. You got it when a is greater than 0. When a is less than 0, you have an advancement. Similarly, here also you will get maximum value when omega is equal to 0. When omega is equal to 0, you will get a minimum value, and when omega is equal to pi, you will get a maximum value. Here you got maximum value when omega is equal to 0, and minimum value when omega is equal to pi. So when you are assuming a is less than 0, the reverse thing will happen. So this is the plot of first problem, that is magnitude and phase plot. With this the first problem is over. We are going to discuss second problem. Second problem says, you can even wonder, so these kind of problems we have discussed in Fourier transform and Laplace transform. Yes, of course, the same set of problem what we have discussed in Laplace transform, Fourier transform, that is in second and third. I am repeating the same problem, but here we are discussing for discrete time signal. Okay, so if you have some good idea about Fourier transform and Laplace transform, then it is very easy to proceed further with discrete time Fourier transform and Z transform. The same kind of problems we are going to discuss in Z transform and also discrete time Fourier transform. Only thing is, you have to be very thorough in Fourier transform and Laplace transform. That's why I am repeatedly saying, so you have to be very careful, and also if you have very good idea about Fourier transform and Laplace transform related problems, you can easily follow this lecture. Now here this problem says, the given signal is x of n, which is equal to a per magnitude of n. A is less than 1. We are going to determine Dtft of x of n. Okay. Now, so we have formula to find out a Dtft. X of e power j omega is equal to summation n is equal to minus 50 plus infinity x of n into e power minus j omega n. Now I am going to substitute x of n in this equation. The x of n is a power magnitude of n. Okay, the rest of the thing is same. Now magnitude of n means it includes both negative and positive values. Negative values and positive values. Positive value in the sense it will start from 0 to infinity, it will go up to infinity. Negative values minus 1 to minus infinity. So I am going to rewrite this equation like, I am going to separate into positive and negative part. Summation n is equal to 0 to infinity a power n into e power minus j omega n plus summation n is equal to minus infinity to 1 a power minus n and e power minus j omega n. Listen carefully. Here a power n only takes positive values, and here also I have a power minus n, it will take negative values. Okay, minus infinity plus infinity. Now we need to find solution to these two summation. So there is no problem with the first equation. So we can easily reduce this equation like 1 divided by 1 minus a into e power minus j omega. Directly we can substitute the value of discrete time Fourier transform for the first term. What about second term? We have negative values. For that, what I am going to do is I am going to substitute m is equal to minus n in the second summation. In the second summation, I am simply substituting m is equal to minus n. What will happen is, when I am substituting m is equal to minus n, the value n is equal to minus or plus infinity will be changed to m1 to infinity, as well as a power minus n is equal to a power m. That's it. I have not done anything. I have simply substituted m is equal to minus n. So when I am substituting m is equal to minus n, for example, if I am considering n is equal to 1, so I have two limits, n is equal to minus 1 and n is equal to minus infinity. I have two limits. When n is equal to minus 1, m will become, because I have assumed m is equal to minus n, m is equal to minus of minus 1 is 1, and for this case m is equal to plus infinity. That's it. M is equal to plus infinity. I am simply substituting the value of n in this equation. So in this equation I will get two limits starting from 1 to infinity. So I have changed the limit by simply substituting a variable m is equal to minus n. Now I have two equations. For that I am going to find solution. For this equation, the first equation, the solution is 1 divided by 1 minus a into e power j omega. For second equation, I have the series starting from 1 to infinity. What I am going to do is I am going to take a into e power j omega outside. When I am taking a into e power j omega outside, I will get the same series. Okay, so I have taken a into e power j omega outside. Okay, and when I am expanding it, I will get the same series. Hence I will get a into e power j omega divided by 1 minus a into e power j omega. Now I have in denominator I have two different terms. One is 1 minus a into e power j omega minus j omega, and 1 minus a into e power j omega. Now I have to reduce it by taking common factors. Here common factor is common, we don't have common factor, common equation. So I am going to multiply the denominator and I am going to cross multiply it. I will get, when I am doing like this, I will get 1 minus a square divided by 1 minus 2a into cos omega in plus a square. So what I have done in the previous slide, I have simply derived the equation. So I told you that I have two equations. One is 1 by 1 minus a into e power j omega, and another equation is a into e power j omega divided by 1 minus a into e power j omega. So I have taken the denominator, I have simply multiplied, and I cross multiplied the denominator in the numerator. So here I have to multiply 1 minus a d power j omega, this one, and here I have to multiply this term, cross multiplication. I will get 1 minus e power 1 minus a into e power j omega plus a into e power j omega into 1 minus a into e power minus j omega. So I have to multiply a into e power j omega inside this bracket. I will get 1 minus e power j omega into a plus a e power j omega minus a square into e power j omega and e power j omega. So e power j omega into e power minus j omega will become 1, because when you are adding these two things you will get 0. E power 0 is 1, and you can even cancel these two terms because minus and plus. So the remaining term what I will get is 1 minus a square divided by 1 plus a square plus 2a into I have a separate have two terms, that is minus e power j omega plus e power j omega. So I have to reduce this into cos 2 omega. So this is the proof for the equation given here. Now we have to plot magnitude and magnitude response, in fact. So before drawing magnitude response for this particular plot, I am going to draw the sequence, that is x of n is equal to a into magnitude of n. It means, and also I have a condition on this a is a should be in between 0 to 1. When a is in between 0 to 1, for negative values of n, I have a growing exponential, and when a is when positive values of n, I have decaying exponential, and you have to represent in terms of samples by considering n is equal to 0, 1, 2, 3, and etc. for any values in between 0 to a. For example, you can even consider 0.5, a is equal to 0.5, and you have to substitute n is equal to 0 for all. You will get the maximum value is 1, and slowly it will get reduced when n is less than, when n is greater than 1, greater than 0, and when n is less than 0, the value of x of n will slowly get increased. Now we have to plot magnitude response of the Dtft we have taken for this particular signal. So I have 1 minus a square divided by 1 minus 2a into cos omega plus a square. We have to give different values to this omega, and we have to draw the magnitude response. And you can even ask me, why don't you are not plotting phase response? By seeing this equation, I find only real part and I don't have any imaginary part. Okay, if it is a complex number, then we can separate into real and complex. Now complex part, here it's we have only real part, hence phase plot is equal to 0. There is no phase plot for this particular case. Now I am going to give different values this omega, and I am going to plot magnitude response. For example, when I am substituting omega is equal to 0, what will happen is cos 0 is equal to 1. Then the denominator part will be something like 1 minus a 2a plus a square. I can write this 1 minus a plus a square like 1 minus a the whole square. So numerator I have 1 minus a square. I can decompose this 1 minus a square into 1 plus a into 1 minus a. I can cancel 1 minus a from numerator and denominator. The remaining part is 1 plus a divided by 1 minus a. This is the maximum value of this particular equation. At the same time, when you are substituting omega is equal to pi, this term will become 0. What I will get is this term will become 0. Hence, I will get 1 minus a square divided by 1 plus a square. So this may be my minimum value. Okay, minimum value. So something like that, the maximum and the minimum value will change accordingly for this particular case. Now we are moving to next problem. Here we are going to find Dtft for a rectangular pulse. So I am just reading the problem. Consider the rectangular pulse defined using this equation, that is x of n is equal to 1 when magnitude of n is less than or equal n1, and 0 when magnitude of n is greater than n1, it means this signal is defined over minus n2 plus n, that's it. So if n value is greater than n1 and minus n1, then the signal value is equal to 0. Now we need to find out discrete time Fourier transform of this x of n and plot the response. This is a job given in this particular problem. Now we do not know anything about this n, this n1. This n1 may be 2, 10, 100, 1000, etc., etc., and we do not know anything about this n. In order to make you understand, what I have done is I consider n1 is equal to 2. n1 is equal to 2. It means it consists of only 5 samples starting from minus n to plus n, and the rest of things is equal to 0. For this special case, this is not the case for all n1. n1 may be any value. You can take anything. Okay, it may be 2 or 5 or 100 or 1000. In order to make you understand, I have considered n1 is equal to 2. n1 is equal to 2 means the sample is available only up to n1 and minus n1. Okay, I have only 5 samples. The rest of thing, x of n is equal to 0. For this particular case, we are going to find solution for this problem. For that, first step is to write Dtft equation. Dtft equation says x of e power j omega is equal to summation n is equal to minus infinity to plus infinity x of n and e power minus j omega n. Now we are going to substitute the value of this x of n, which is given in the problem. So the problem, from the problem, I am going to change the range of small n from minus infinity to plus infinity to minus capital N to plus capital N, because the signal is defined only during this interval, and the remaining values of n, the value of x of n is equal to 0. So I am going to reduce the range of values of n from minus infinity to plus infinity to minus n1 to plus n1. Hence I am rewriting the equation like x of e power j omega is equal to summation n is equal to minus n1 to plus n1 e power minus j omega n, because the value of x of n is equal to 1. I have not mentioned the value of x of n is equal to 1. If you want, you can write like this: 1 into e power minus j omega n. Okay, now this is again a peculiar problem, because the limit starting from minus n1 to plus 1. But if we have been seeing formula starting from n is equal to 0 to infinity, something like that. But we have a special case starting from n value is equal to minus n1 to n2. Hence, what I am going to do is I am going to make one-sided summation by simple substitution. So what I am going to do is I am going to consider a dummy variable m. This m is equal to, I am assuming this m is equal to n plus n1, and I am going to find lower and upper limit of this m by substituting lower and upper limit. So first I am going to substitute m is equal to minus n1 in this equation. When I am substituting m1 n is equal to minus n1, m becomes 0. This is the lower limit. At the same time, when I am substituting n is equal to capital N1, then m value will be 2n1, and also I am going to find out the value of n. So n is equal to m minus m1. So I am going to substitute all these new values in this summation. When I am substituting the new values, I am going to replace n with m. So m value, the lower value of m is 0 and upper value is 2n1, and I am going to replace this n by m minus n1. That's it. So I have a limit, I have a range of summation from minus n1 to n plus n1. It is not n2, this is n1, okay? This is not n1, this is n1, this is not n2, this is n1, okay? Now I am going to change the range of n value by simple substitution. Now what happened is, I am here when m is equal to 0 to 2n1 e power minus j omega m minus n1. Okay, now I have two terms in this exponential. I am going to separate it because one term is variable, another one is constant. I am going to take constant outside. Here, for this particular case, when I am separating this e power j omega, this equation, I will get e power minus j omega m into e power j omega n1. So this term is constant one. I am going to take outside. So I have taken this e power j omega n1 outside, and remaining one summation m is equal to 0 to 2n1 e power minus j omega m. And we need to find out solution for this equation. Of course, we have a solution for a infinite summation, that is summation n is equal to 0 to infinity x power n, means we can reduce that equation into 1 by 1 minus x, but we have limit from 0 to 2n. For this we have to find a solution. For that I am going to do small a simple mathematical manipulation to find the solution. What I am going to do is I am going to expand this series. This is summation, that is e power j omega n1 into, I am simply expanding this series like 1 plus e power j omega, that is n is equal to 1, m is equal to 1, m is equal to 2 e power minus j2 omega plus, and it will go up to e power j2n1 omega. It will go up to j2n1 omega. Now what I am going to do one modern addition and subtraction of this equation. What I am going to do is I am going to expand this equation, and I am going to write up to infinity, and I am going to subtract what I am expanding. Okay, for example, you take this equation, what this is the real equation, this is up to the real equation. After this equation, what we have, I am going to add e power minus j 2n1 plus 1 omega, and I am going to extend up to infinity, and I am going to subtract. So I am adding and subtracting it. Listen carefully. I am going to add something, and I am going to subtract the same value in this equation. So I am simply adding and subtracting the same quantity to solve the problem. Okay, like 1 plus 2 minus 2, the value is same, is equal to 1. Okay, there. So in such a way that I am adding and subtracting. After adding and subtracting, okay, after adding and subtracting, what I am going to do is, so here this series is first series. So this I am going to take this first series. The series is starting from 1 and it will go up to infinity. So hence I can reduce this equation like 1 divided by 1 minus e power minus j omega. E power minus j omega. I am going to simply reduce this equation like 1 minus e power j omega. Similarly, I am going to do the simple manipulation the next slide. So first series I am reducing into 1 divided by 1 minus e power j omega, because the series starting from 1 to and it go up to infinity. The second series I have taken, I am going to take e power minus j 2n1 plus 1 omega outside, that is from this expression. From this expression I am going to take this particular exponential outside. When I am taking this exponential outside, I will get this expression 1 plus e power minus j omega plus e power minus j omega, and it will go up to infinity. Now I got the same format, 1 plus e power j omega, and it will go up to infinity. I can easily simply reduce this infinite series into 1 divided by 1 minus e power minus j omega. Okay, now the complex problem reduced to simple problem. So first I have a series, I am reducing into 1 by 1 minus e power minus j omega. Second, also I have a infinite series, I am reducing into 1 divided by 1 minus e power j omega. Now we have to cross multiply and find the solution. That's it. So here the common part is 1 divided by, sorry, common part is e power j omega n1, and inside the bracket I have two terms. For two terms the denominator part is same, so I am taking 1 minus e power minus j omega common, and I am going to combine the numerator term. The numerator term is 1 minus e power minus j omega into 2n1 plus 1. Now in order to make simplify the equation, and I'm small announcement to you all, I'm going to continue next hour also, because your faculty member not available today. So I'm going to continue today's class. Today, I mean third class. My fourth hour will be taken by Dr. Sunil. Afternoon hour. Okay. So I'll give a break at 11:50, and all of you once again join the class at 12 o'clock. Now, so I'm going to do a small manipulation. What I'm going to do is I'm going to multiply e power minus j omega by 2. I'm going to multiply and divide this e power j omega by 2, the numerator and denominator of e power j omega n1. First thing, so I'm simply multiplying. When I'm multiplying, what will happen is, these two are exponential. I can combine these two exponential like e power j n1 plus 1 by 2 omega. Okay, I am simply combining it. After combining these two exponential, I am simply multiplying this exponential inside the bracket. When I am multiplying this equation inside the bracket, I will get e power j n1 plus 1 by 2 omega minus e power j n1 plus 1 by 2 omega into e power minus j 2n plus 1 into omega. So I have two exponential, and I have to combine these two exponentials. The common term is n1 plus n, important term is common term is omega, and the variable one is n1 plus 1 by 2 and 2n1 plus 1. So I am simply combining these two things here, that is n1 plus 1 by 2 minus 2n minus 1. When I am adding all these factors, I will get minus n1 minus 1 by 2. I am adding all these variables, and when I am comparing these two things, what I will get is e power j omega n1 plus, the same term, there is no change in the first term, and second term, these two terms will be combined, and I will get e power minus j omega n1 plus 1 by 2, and there is no change in the denominator part. I have simply multiplied e power j omega by 2 inside this bracket. I will get e power j omega by 2 and e power j omega by 2 into e power minus j omega. When I am comparing these two things, I will get e power minus j omega by 2. Here, this is something like e power j theta minus e power minus j theta. So e power j theta and e power minus j theta by 2j is nothing but cos theta. So what I am going to do is, I am going to multiply and divide by value 2j. So I am going to multiply and divide by the value 1 by 2j. When I am doing this, the numerator part will be equal to sine omega n1 plus 1 by 2, because n1 plus 1 by 2, and denominator part I have sine omega by 2. So this is the solution of given problem. X of n is equal to a power x of n is equal to 1 into 1 over defined over uh, as interval magnitude of n is less than or equal capital N1 and 0 otherwise. This is a solution. Now we have to draw magnitude response for this particular problem. So this is nothing but graphical representation of given problem, and this already I have given in the previous slide. Now we have to find the maximum and minimum value of this expression, that is x of e power j omega, by substituting different values to this particular equation. When I am substituting omega is equal to 0, so the term will attain maximum value when omega is equal to 0, and the expression will slowly get reduced, and it will reach the negative value when pi is equal when omega is equal to is greater than pi by 2, and when it reaches pi, omega is equal to pi, it will again go to positive value, and the term will have positive and negative value alternatively, depends upon the value of omega. So this is the magnitude plot of the given problem. With this, I am stopping, and I am giving a small break to you people. Okay, all of you can join the class at 12 o'clock. Thank you very much. We will resume once again.